Hello, everybody. Welcome to Water and Major Minerals. We're now up to Chapter 4 for our Human Nutrition class. This is, again, a bit of a longer lecture, so we're going to break it up into two parts. Some of the important things that you're going to need to know, we're actually going to start out with water and thinking about what influences water balance and how does the body maintain water balance. It's actually very important for normal physiological function. We're going to also talk about dehydration. So how does dehydration develop and the opposite of dehydration, which is water intoxication, develop, and who is likely to get these two things? They're both very dangerous. Then we're going to shift in with water and then all of the major minerals that we're going to discuss in this class. We're going to need to know all of the important food sources, major functions, problems with low and high intake of the major minerals, and how to avoid inadequate or excessive intakes. So that's a very long objective. Lot of different facts that you'll need to know about the minerals we discuss. This is exactly the same as what you needed to know about the vitamins. With minerals, we're going to go into some of the disease states that are associated with mineral status. Specifically, we're going to have to know about hypertension and osteoporosis. So for hypertension, we'll link that up with sodium, with osteoporosis, with calcium. So for both of those diseases, what's the major cause? What are the risk factors? So what puts someone at more risk? And what are the treatment options? So a little bit of introduction as we think about water. Water's kind of a funny category. It is an essential nutrient. We need it in large amounts, but it's not really considered a macronutrient because it doesn't have energy. It's not a micronutrient because you need it in large amounts. We're going to talk about it here with minerals because some of the minerals are important in maintaining water balance in the body. So to give you a sense of how important water is, if you look at these pictures showing a female and a male and think about what our body is actually made of, right? We're not just jellyfish. We actually have different components. But for both males and females, we are mostly made up of water, with men having a little bit more body water on average than a female. Women tend to have more body fat, and that's mostly to support reproduction. Women are able to get pregnant. Men have a little bit more protein. They generally have a little bit higher muscle mass. And then we also have minerals. Think about what makes up our skeletal system, our bones, and some other nutrients in very small amounts. So if we take a deeper dive into water, you can think of it as two different components. We have intracellular fluid, which makes up 2/3 of our body's water, and that is intracellular. So it's all of the fluid inside a cell. Extracellular is all of the fluid that surrounds the cell on the outside. So specifically, that is interstitial and intravascular water. And water content does vary. It's not the exact same for everybody. We report the averages. It varies by age for sure. As we get older, our body water decreases, and by body composition, muscle tends to hold on to a lot of water, for an example. So water is not just water in the human body. Body fluid also contains something called solutes, excuse me. And particularly important are electrolytes, which is a specific type of solute in the human body that we often divide into two categories, cations and anions. And that will be whether or not it has a positive or negative charge. And here's why we throw water in with the minerals. Some of the important solutes in our body water are in fact minerals. So we'll talk about potassium and magnesium, phosphate, sodium, calcium. Those are all important minerals. Excuse me, I wasn't done with that slide. So major cations, again, that means it's got a positive charge, where an anion will have a negative charge. Some of these are dissolved in the fluid intracellular, and some of them are in our extracellular fluid. So a little bit about how the water maintains, or how the body maintains water balance. So very simply, we have a large part of our human body is made up of water. Why does it stay where it needs to? Why doesn't it move around and get into places where it should? There's a couple of physiological mechanisms that allow that to happen. The sodium potassium pump happens to be one of them. So both sodium and potassium are minerals. They're both have that positive charge. Potassium is a intracellular cation, where a sodium is an extracellular cation. And this might seem like you don't know what you're looking at, but you do actually. You know what this is. You can see the phosphate with the lipid tails. So this is a cell membrane. This is a protein pump. So this is made up of specific amino acids that give it a particular shape that's able to bind, in this case, electrolyte sodium, potassium, and sodium, and allow those electrolytes to move in and out of the cell. So that's very important in making sure the balance of sodium and potassium is correct. Fluid will follow these cations, and that's one way that we maintain sodium or water balance in the body. Another mechanism is simply osmosis, and you've probably learned about that a long, long time ago. I like these pictures. I think it explains it very well. So you're looking at a cell, and there's the nucleus right there. And here we have a case where there's a higher concentration of solutes. So there's something that's being dissolved in this extracellular fluid that's caused it to become very concentrated, and the concentration inside of the cell is much lower. So physiologically, this is not balanced, right? We have a higher concentration out here. So osmosis is the movement of water to try and even that out. So if you add more water to the outside, it will become more diluted. There'll be now less water in the cell, but now we get to this nice even balance where the concentration is the same both in and out of the cell, which is generally how the human body likes to be. So we have these mechanisms in place to keep water where it should be. It should give you a clue that water is pretty darn important, and in fact it is. If you were in my class, I made this point quite a bit at the beginning of the semester. You can't survive without water. You get dehydrated. Think of that person in the desert that doesn't have a water source. They are not going to last very long. So it's obviously extremely important. So a couple of sort of facts to bring home that point. We need water. It's not only part of our, a big part of our human body. It makes up a big part of our brain, which is a pretty important organ. We need water to regulate our body temperature. If it gets too high, think about if you have a fever, you become too hot. One of the things that happens is that you sweat. That's your body trying to cool itself off. All of those important things, even something like an enzyme, protein is not going to work if it's too hot. So you really have to keep your body temperature within a certain range. Makes up a big part of our blood. Without our blood, we couldn't transport oxygen and nutrients, removes waste. If we weren't able to remove waste, things would build up and become toxic. We always think of our bones as sort of hard minerals, but there's in fact fluid as part of them. Helps cushion our joints so we're not always getting hurt. We kind of talked about this with the blood, moistens oxygen so you can breathe it better, helps convert food to energy, which we need in order to survive, protect and cushion our organs, help with absorption of nutrients, and make up a big part of our muscles. So lots of functions. We get water from drinks, obviously. food and metabolism. It's a byproduct of many of our metabolic reactions. Just keep in mind that some of our water sources do have extra calories. And some of our beverage choices, people don't often think of calories from things that they drink, but they can actually be quite high. You can look here, some beverages with high calorie amount, juices, coffees with a bunch of cream added, alcohol, um, will all add extra calories, whereas plain water, of course, is 0 calories. Here's just the water content in certain foods. Some of them are obvious, right? Like beer is a liquid, so obviously the water content is going to be extremely high, almost 100%. A lot of our fruits and vegetables are very watery. So again, we can get a pretty decent amount of fluids from our foods, especially if we're doing a good job with fruits and vegetables. How much water you need will vary with your body size, your level of physical activity. The more sweat, the more water you need. Environmental conditions, if it's hot and humid, you'll need more water. And of course, I just mentioned dietary intake, how much you get from your foods. So the adequate intake for water, we don't have a functional marker, so we have an AI, is 15 cups for men and 11 for women. Now, you might be thinking, I've always heard it's 8 cups, and that is a good average. Keep in mind that this is total intake, so it also includes fluids that we get from food. When you hear 8 cups, it's just talking about this part, the 80% fluid intake. Now we tend to balance our water, right? So if you drank 8 cups of water, you had enough fluid in the foods that you eat to equal about 2 cups. You also produce another about 1.25 for metabolism. Um, we need that water on a daily basis because we lose water on a daily basis. We sweat, some of us more than others. When we breathe out our carbon dioxide, we're losing some water in our breath. Think about if you exhale on a cold day, you can actually see that a little bit better. We certainly urinate, so we're eliminating quite a bit of water that way, and we lose some water in our solid waste as well. So what goes in comes out, which again is why we have to keep our fluid intake up on a daily basis to be healthy and not get dehydrated. That does lead me to a deficiency of water, which is called dehydration. I'm sure you've all heard that term before. It's simply defined as when your fluid output exceeds your fluid intake. So you're losing more water than you're taking in. This is most likely to happen in cases where people are either need more water or they're losing water because of an illness or something else. So diarrhea, vomiting, especially if it's excessive, will cause dehydration because you're losing so much extra water. Fever because you'd be sweating more. Lots of exercise, hot, dry weather, and high altitude because of the difference in the way you breathe. So you probably remember this from sports nutrition, but for every pound you lose during exercise, you want to replace that with 2.5 to 3 cups of water per pound to maintain hydration. If you're wondering what the heck this is, this would be the P-test. So a simple way to kind of tell if you're dehydrated, you want your urine to be nice and clear. The darker that is, the more concentrated your urine is, um, meaning that you are getting dehydrated. I will point out if you take a multivitamin, some things, especially riboflavin, that water-soluble vitamin, shows up in your urine. It'll make it kind of a funny color. So the P-test doesn't always work if you're taking, especially a multivitamin. This is an important thing to think about, to remind us how dangerous dehydration can be. So this is just looking at your percent body weight loss. So this would be, if you lose 10% of your body weight due to fluid loss, that's incredibly dangerous. So of course, anything greater than zero is going to start to be dangerous. And the more dehydrated you get, the more danger it is. So you've probably heard that if you're thirsty, you're already dehydrated. So you've already lost about 1% of your body weight when you actually feel thirst. So you are on the road to dehydration. That's an early sign. As you start to lose more and more body water, you're really going to start to feel worse and worse. Here we're talking about getting really thirsty and starting to lose your appetite. Here you're getting kind of sluggish, sleepy, maybe a little bit nauseous. Your nervous system's going to start to feel impacted. You might feel faint or dizzy or have trouble walking, start to get a headache, get really hot. At 8%, you're going to have trouble breathing. It might even seem almost like you're having a stroke. You can't talk very well. You're confused. At 10% and greater than 10%, you're really in the danger zone where your kidneys are going to stop working, and you can die from dehydration. This used to happen every year. I'd always hear a story about this. It was often in August. Um, when football would start. So think about athletes not having, maybe being a little deconditioned over the summer. They start out with heavy physical activity in the hottest, most humid month of the year. They're wearing full pads and might have the thought that, it's kind of macho to not have to drink water. And again, it's incredibly dangerous. Young people could die from dehydration very, very quickly in those types of conditions. So it's a very common problem among everybody, and of course, athletes are a little bit higher risk. You will perform better if you stay hydrated, and you'll be much safer. So what happens when you get dehydrated? The reason why you might faint as you get more dehydrated is your blood pressure is dropping, and that's one of the ways your body's kind of fighting this. And there's a couple of different things that are happening here. So it's very carefully regulated, your blood pressure. So one of the things that happens is your hypothalamus, which is a part of your brain, is always receiving signals, right? That's what the brain does. It gets messages from the rest of the body. It's going to be able to detect that you have increased blood osmolality, right? It's more concentrated because that's part of being dehydrated. So there'll be various receptors that would be able to detect that, send that message to the hypothalamus, which is going to tell the pituitary, which is a really small gland right here on the base of the brain, and that gland secretes hormones. So one of the really important hormones here is something called ADH, or antidiuretic hormone, that's going to be released by the pituitary gland. That's going to now travel to the kidney. Hormones can travel through the bloodstream. Its target organ is the kidney, which is very important for fluid balance. And we're going to have retention. So water is going to be retained within the kidney, so you're keeping water in the body, you're not urinating, and that's going to actually help increase your blood pressure. Um, this is a bit more of a complicated process, but this is also happening when you are dehydrated. So your blood pressure starts to drop from the dehydration. Again, your kidneys are a really important organ for this. So series of events. So you've got renin and angiotensinogen. They are going to work together to make something called angiotensin 1, and that can be converted to something called angiotensin 2. That can act on the adrenal gland, which is this little gland that sits on top of the kidney that's going to make a hormone called aldosterone. That's going to act on the kidney to increase sodium retention and increase water retention and increase blood pressure, right? So we just showed some other hormones on the previous slide. This is just yet another mechanism to get that blood pressure up if we start to become dehydrated. Same kind of initial pathway, but angiotensin 2 not only acts on the adrenal glands, it also acts on the blood vessels themselves. So it's telling the blood vessels to constrict and get tighter, right? Which is going to make harder for the blood to go through, which is going to increase blood pressure. Now, I just sort of warned you a lot about getting dehydrated. Believe it or not, you can actually have too much of a good thing. So water toxicity is incredibly dangerous as well. So instead of dehydration, toxicity or overhydration is called hyponatremia. And in this case, the electrolytes that are in our blood, again, think mostly about sodium and potassium, are too diluted. So they're not concentrated, they're diluted, meaning that there's too much water for those electrolytes to function normally. So if you're suffering from hyponatremia, you'll know it, you probably won't because you'll be really, really sick, but it presents itself as headache, blurred vision, cramps, convulsions, and it can result in death just like dehydration can. We don't tend to see it a lot. Dehydration is far, far more common. It is most common in infants and endurance athletes. So infants, have a kind of a delicate balance in maintaining their normal hydration and dehydration status. Um, when we see hyponatremia in infants, it's often because they're on formula, which is when you mix powder with water for most babies. That's how they get their formula. And if it's not mixed correctly, if there's too much water, that can cause hyponatremia. We also more commonly would see this in endurance athletes, especially before something like a marathon, where the athlete has actually overhydrated to the point where they cause hyponatremia. So I'm just going to quickly introduce minerals here, and then we'll end this for now and go on to part 2 later. So we're done talking about water. We're now going to talk about minerals. So this is now the first time we've talked about something that's inorganic. Everything else we've talked about up to now has been organic. So minerals are minerals. They do not contain carbon. That's what makes them inorganic. Like vitamins, we need them in very small amounts. We have 2 major categories. So we have major minerals and we have trace minerals. Kind of generically, how are minerals absorbed? Minerals, a lot of them can be toxic, so the body actually kind of regulates absorption very carefully. And often it's based on physiological need. So if you're low in a certain mineral, you will actually absorb it better. Whereas if you have a good amount, if you've been eating a lot of it, for example, and you don't need much more, you won't absorb it as well. That's just sort of a physiological protection. Another important concept with minerals and absorption is this thought of bioavailability. This is going to be more tricky with minerals than some of the other things that we have talked about. So bioavailable just means, you might have consumed the mineral, it's there, but bioavailable means, is it in a form that the body can actually use? And bioavailability with minerals is impacted by a lot of things. That's what this list is here. So some minerals compete with each other for absorption. So if you're eating, a lot of iron and a lot of zinc, they're going to compete and they will limit the absorption of one or the other. They also compete for absorption with non-minerals. So one of the things that sort of tends to bind up minerals and make them less bioavailable is fiber. Oxalate, which is a compound that's often in coffee and tea, can bind up minerals and make them less bioavailable. Same with polyphenols. And some things actually enhance mineral absorption. The most common example is when you have vitamin C, a water-soluble vitamin, with iron, you actually absorb the iron better. Here's our two main categories. So our major minerals are calcium, phosphorus, potassium, sulfur, sodium, chloride, and magnesium. And that's where we draw the line. Our trace minerals, it just simply means that they are found in smaller quantities in the human body. So you can see we have quite a bit of calcium, right? 1,200 grams in the human body. Whereas iron is a trace mineral, we only have about 10 grams, and then it gets even smaller, manganese, copper, and iodine. Another kind of generic fact about minerals in terms of function, a lot of our minerals are important for water balance. That includes sodium, potassium, calcium, and phosphorus. Some of our minerals help transmit nerve impulses. That's sodium, potassium, and calcium. Some of them are enzyme cofactors, so they work with enzymes for optimal functioning of the enzyme. Some of our minerals are direct components of body compounds, and some of our minerals are required for normal growth and development. So we'll take a little break here and then we'll come back and go over the major minerals.